Great. Good. So today we are continuing the class. So how was the whole thing? We talk about essentially some kinds of basic covering problems. Then we talk about connectivity and cut problems and how can we solve one the most simplest graphs, mainly trees. There we can, in trees, we can solve lots of problems in polynomial. Here we want to go but we consider general graph, and generally we pay this log n factor because of embedding into trees at least. Here we want to see, can we get better algorithm like constant or even 1 plus epsilon? We talk about several constant algorithms later in this class that actually you can solve this problem using this general approach, but you can also get it more efficient way that you don't pay this log n. But here for some graphs, which are interesting graphs, these are planar graphs and generally H-minor free graphs that I will define, and even more general than that. These are some kind of a sparse graph for which we can actually get, let me just make sure. Yes. So for these graphs, we are getting for this graph, we can get not only constant, but lots of case PTAS. And what is the PTAS? PTAS essentially is 1 plus epsilon for any small epsilon, for any small constant epsilon greater than 0. So we can guess it's 1 plus epsilon for all of these things. These problems are also NP hard on this graph. So that's the best essentially that we can hope. So PTAS is somehow the best that we can hope, and we will get it there. And we want to say again a general framework. So we talked about lots of frameworks so far, even like about submodular cover or other versions of essentially set cover or generalizations or unique coverage. Or this, all of them are like frameworks. Frameworks are great because these are something that if you know about these frameworks, then these are like a hammer that you can kill any particular problem. You don't need to just consider a particular problem and solve on it. We will talk about some other particular algorithm, but still even their approaches are very general, can be used for other things. That's the thing that we talk more about. Good. But here, today we talk about it, and one of the most important ones that actually subsume lots of previous results are bidimensionality and by products. These are like essentially the state of the art almost for planar graph. If you know that, if you know this theorem, then you can go planar graph. Lots of people don't want to touch planar graph because they don't, they may not aware of this theorem and they feel good. But these are, again, lots of essentially abstraction, lots of details has been used such that you can get such kind of nice theorems. And what is the thing that we are talking about? The main idea, this bidimensionality, why do we call it bidimensionality? It comes from the grid. Essentially, we say that planar graphs, more generally bounded genus graphs, and H-minor free graphs, these are actually can be quite complicated graphs, but they are somehow equivalent of the grid. And the whole bidimensionality, in short, is that if you want to solve one of these problems, see whether you can solve them efficiently on grid. If it is the case, then you can solve it in this general graph. Otherwise, at least this approach does not work, or there's not, lots of these results are so tight. So if it does not work, maybe you cannot get anything better. Grid is a special case of planar graph because it's this is the grid, R by times grid essentially. Yeah. So, but this is again very high level ideas. We will talk more about. That's the whole concept essentially. Again, that has been obtained through lots of papers. The same thing that we have seen for Bartal. The same thing here. Even probably more papers has been done. And these are like some of the things that subsumes everything. Good. So let's say a little bit about so we know that lots of problems are NP hard problems. And of course, some instances like planar graphs are very useful, and generally some generalizations of that. And what is a planar graph? So planar graph in general is a graph that you can draw it on the plane such that no two edges are essentially intersecting. That's like, for example, this is a K4, complete graph on 4 vertices, that you can do it essentially. But K5, you cannot do that. So you cannot, if there are, this is like you see, this K4, K5, you cannot draw it on the plane without any crossing. However, K5, you can do it actually on bounded genus graphs. What is the meaning of bounded genus graph? Essentially, when you consider a torus, like for example, a tube, consider a tube, can we draw it on that one? In that case, for example, K5, you can do it now. And this is like the torus. So this is like the thing that it is something like this. And then sometimes essentially, planar graphs, essentially plane and a sphere are the same essentially. But more general than that would be a torus. And more general than that would be essentially a torus with 2 holes essentially. Or 3 holes. Yeah, you can always say that the outside one would be the outside of a sphere. Essentially.
Like the sphere, you can go left and right.
Yeah, but you can this is you can actually so you can improve it more formally. But the issue is that the sphere, you can also open the sphere essentially and put it on the plane. So it's something, a sphere is more general than plane. But you can say that if something you can do it on a sphere, you can also open from some parts of it and do the same. Just see the way that they are doing essentially for the map of the board essentially. So you can always open it and put it in the plane. But then more general would be, so this is the genus 1. This is genus 3. And so on and so forth. We say bounded genus. And that is important because of the bridges. The bridges are the one that essentially make something like road network generally is a planar network, except there are some bridges. These bridges, essentially, you can consider them as this kind of genus that you are increasing the genus by constant. Good. We talk about.
Let's say
not. You need to be careful. Not necessarily the case, but there. In terms of practicality, yes, but you should be careful because they have exact mathematical definition. That would be more like essentially H minor free graph, the next generalization that has this one. Because if this is the intersections, if a small number of intersections, yes, but you might have still lots of intersection, but in different places, then you may actually do it with H minor free graph, as we will talk about. So approximation algorithms. Here we are talking about PTAS, and we want to get within some constant factor C of the optimal solution, and it is PTAS if it is 1 plus epsilon for arbitrary constant epsilon. Sometimes this epsilon actually even for non-constant works essentially. We talk about fixed parameter algorithm. So essentially it is a problem which is parameterized by a parameter P, and P is typically the cost of the optimal solution. For example, I think this is the example that I always say that you want to see, this is a city, you want to say, can I create essentially 5 fire stations such that everyone is within the distance, reasonable distance from each one of these fire stations. So in this case, one possibility is that you might want to run essentially all possible, if there are n places in the city, you may want to try all n places. The running time would be n to the 5. You want to get essentially algorithms which are much better in that sense. So you may want to get something like maybe 2 to the 5 times n, or in general, 2 to the k times n. These are the fixed parameter algorithms that we are talking about it. And this is exactly the thing that we have. So we want to get some running time. The running time is f of p. This can be, some exponential time, because the problem is NP hard. We cannot expect that we can get it essentially one polynomial. So f of p, it can be 2 to the p essentially. But you want to get to n to some constant. This constant should be independent of the parameter. And this is essentially equivalent of, you can say, f of p plus n to the order. And interestingly, I mean, there was some of the things that this bidimensionality is doing. You said that this kind of, for this problem, lots of fixed parameter algorithms the people obtain, some of these PTASs that they obtain. And this bidimensionality essentially says that all of them comes, like they are essentially the same fact, the same phenomena. All of them comes from the fact that any planar graph or this generalization, we can approximate them by a grid. And that's essentially the whole idea. And again, there are lots of work. Lots of them are actually quite complicated, but that gives you somehow the ideas about this. And here, we talk about this bidimensionality. And again, bidimensionality means that on a grid, essentially, we are talking about the bidimensions. And we aim for general algorithmic framework, the same thing that we have seen so far for essentially embedding into trees. And here, in some sense, in some versions of that, we are embedding into a big generalization of trees, which are bounded Treewidth graphs. Let me define what's the meaning of minor. So this is all essentially planar graph. And as I mentioned, this is a bridge essentially that you may talk about. I talk about planar graphs. I talk about the bounded genus graph, the graph that can be drawn on this kind of torus thing. So this one has say 3 holes, so it has genus 3. Can we draw a graph on this essentially torus things without intersecting any 2 edges essentially? The edges can only intersect at the endpoints. And more general than that is this essentially the concept of H minor free graph for a constant H. So a graph G has a minor H if H can be formed by removing and contracting edges of G. So consider this G. You can do one of these operations. You consider each edge, you can either delete it or you can contract it. Contract means essentially take these 2 vertices and then make it 1 vertex, and any edge that essentially attached to one of them, you will just put it. So you will remove also multiple edges. So if this guy also has something like this, then you only keep one of these edges. And here, for now, we are talking about unweighted graphs. So if from G, you can do this operation and get a graph H, then we will say that H is a minor of G. That's actually a very interesting thing, and there's a huge theorem it's there that I will talk more about it by Robertson and Simon. So H is called the minor of this. Again, you can get from G from H either by deleting. I mean, we are assuming the graph G and H are both connected essentially here. When you talk about deleting edges, you can also delete vertices. So if G exclude H as a minor, then it's called H minor free graph. If you cannot from G by this operation, you cannot get H, then you will say that G is H minor free graphs. Does not have such a minor. And this actually comes from planar graphs, which are, this is a Quadratically theorem essentially. It said that planar graphs are both K3 and K5 minor free graphs. So they are simultaneously, they don't have any K3. If the graph is planar, you cannot make a K3, and you cannot make K5. And this is if and only if. Why? Because K5 and K3 also, you cannot draw them in the plane without any crossing. So this is essentially characterization of planar graphs. Any graph that does not have as a minor K3 or K5, then essentially this graph is a planar graph. And why these are interesting? This is important because in some sense, this is similar to this kind of concept of NP, that here you want to give evidence, essentially. So, okay, what's the meaning of NP? That if I give a solution to you, we can check it in polynomial time, which is a solution or not. It's verifiable in polynomial time. The same thing here. Here it said that if the graph is not planar graph, I can produce some essentially a minor for you that it is K3 or K5. This K3 or 5, these operations that we are doing actually does not change planarity. So if the graph is planar, under these minor operations, both deletion and contract still remains essential. So I said from G, I can create this K3 for you or K5 for you. That's the proof that this graph is not a planar graph. I mean, not that you may not have a, I mean, this is a graph is given to you in terms of graph. You don't know whether it is planar or not. To check whether it is planar or not, you say that if I can give you a K3, which is a minor of these things, so this is the proof that this graph is not a planar graph. And this is the reason this kind of minor becomes important. What is the idea? The idea is that lots of these properties, which is we define it minor closed properties, that this is a big theorem essentially, so that if the property is minor closed property, then I can find a finite set of minors for you that the graph satisfies that property if and only if it does not have any of these minors. This is quite non-trivial things essentially. Come from this fact, this is actually Wagner's theorem essentially, that Robertson and Seymour that proved this. Said this is like this thing there. And by the way, what is the meaning of minor closed property? We will talk about it. But generally means minor, something closed means that if you do the minor, it has this property P, after the minor it still has the property. For example, polarity is a minor closed property. Polarity is a minor close because if the graph is planar, if you delete things or contract an edge, still it remains planar. So it means that polarity is a minor closed property. By this theorem of Robertson and Seymour, he said that there is a finite number of minors that I can, and constant size minor depends to this definition of this property, but everything is constant. I can give you this such that if the graph does not contain as a minor one of this graph, then it satisfies that property. And this is a quite non-trivial theorem. So this kind of essentially minor closed property can be described by a finite number of minors of constant size. And the other thing, which is that also comes from this fact, this is actually this another interesting thing, that if you have essentially a sequence of graph G1, G2, G infinity, there is, you cannot continue this until infinity unless this happens, that there is I less than J, that Gi is a minor of you cannot have an infinite sequence that none of them is a minor of each other. At some point, one becomes a minor of them. This is essentially the Wagner's conjecture that is, it's a huge proof for that with Robertson Seymour. It is like, I think it is 30 pages. Some of these papers are like around 40 pages. So I think maybe there are some introductions, etc. But the whole theorem, this is the deepest theorem essentially in graph theory. But the proof is like over 500 pages. So this graph minor theorem, this theorem, these two things that I have mentioned, very easy to describe. Any minor closed property has a finite number of minors, constant size essentially, that you can describe it, you can characterize it. And these two are actually comes also lots of that one and this other theorem that I mentioned. If you have an infinite set of graphs, then one should be the minor of the others. These two, essentially the 500 pages essentially for proving these two theorems. A little bit more extension of that, but that's the main thing. And they published over almost 30 years. They obtained it actually originally in this one, but it took almost 30 years to publish the find. Like from 1990 to, I think 2010, some of them later got. They had the proof, but of course, I mean, they had the proof. I mean, this is like archive version. This to get it in the journal, it takes that much time because because this has been divided into, as I mentioned, like around a series of 25 to 30 page paper. All the same authors. Robertson and Seymour. Good. So I worked actually with Seymour, and he's probably, the best living person who can do graph theory, especially this kind of case analysis. He's the master of it. There is no one comparable to. Okay, so I think a similar series of more than 20 papers. I think it's more than more closer maybe to 30 now because they published a few more since they had this one. But this is Robertson Seymour, 1984. And as I mentioned, this is the powerful result on excluded minor. Every minor closed graph property preserve, as I mentioned, the minor closed property means that if you take the, if a graph has this property, if you take the minor, it still has this property. Has a finite set of excluded minors, essentially. And these are the size of them, of course, is bounded, the size of each of these minors. And this is the Wagner's conjecture. That says essentially what is the implications? Implications that every minor closed graph property can be decided in polynomial terms. Good. So that is very important as well, because we can check whether this is also non-trivial, that you can check whether this is a minor of the other graph. But because of that, essentially this fact that you can represent for any property, I can just give you a set of things that check whether this graph has any of them as a minor or not. This is if and only if to satisfy. So if there's an algorithm to check the minor, so given that, can you essentially, you can check it in polynomial time whether this graph satisfies the property that you have or not. So that's a very powerful theorem, essentially. And this also says that, and we will talk later about it. What is this theorem? This is actually, I think I was among the first people who are using this theorem. These other structural results, the people even didn't know that one, the time that I started working on that one, like around 2001 or something like this. It's very hard, some of this, they are doing that. This is like, some of this this paper, it says that this is, I don't know, graph minor, this is called graph minor 1, graph minor 2, etc. That graph minor 16. You will write in the abstract, this is the abstract. In this theorem, we are proving this lemma that will be used for graph minor 20 or later. And how many pages is this paper? 40 pages. Just proving that lemma. Lots of case analysis. Lots of case analysis.
So you mean like
essentially this theorem that I mentioned here, all of them, if you want to prove them, essentially, if you don't know them, you want to prove it, then you need to consider lots of case analysis. What about this case? What about this essentially, if this happens like this or that? Lots of case analysis, you need to do it on the graph to see whether this has this property or not, essentially. This comes from this fact. These theorems also come from this one. This theorem was used essentially mainly by this bidimensionality thing that we have done it. That graphs minor excluding h have a special structure. They can be drawn on bounded genus surfaces plus some extra features. So that is important. It says that H minor free graphs, which are very general graphs actually. I mean, we don't have that much ideas about them. One thing that we know that this H minor free graph actually a subset of bounded arboricity graphs. And what are the bounded arboricity graphs? These are actually very general sparse set of graphs. A bounded arboricity graph, it says that if you consider, so this, it is called bounded arboricity. So the bounded arboricity has two definitions. One of them, essentially, the one that we are talking, is that if you consider any induced subgraph, so if any V prime, so if you consider any induced subgraph, this, the average degree would be constant. That means it's bounded. So for any induced G of V, the average degree is bounded. Good. So that's one definition. The other definition is that, I mean, essentially you can, this graph has a bounded arboricity, that if you can partition the set of vertices into a bounded number of forests. That's another. This is not clear that these two are equivalent, but these are the same, but they are equivalent. But this is actually the one that we are doing more essentially. You can say that this bounded arboricity, these H minor free graphs are indeed bounded arboricity graphs. Why? Because essentially comes from this fact that you know that in every planar graph, there should be a vertex of degree at most uh, 5 or 6. So I think it is 5 or 6. Yeah, just you can check that, but I think it's 5.
It's 5.
What was that?
It's 5.
It's 5, yeah. So for every planar graph, actually, the degree is bounded by, I mean, this, I've worked on this one when I was fresh on this one, I don't know, 20 years ago. Then this is like, it was the case that almost there was no planar graph that I said that I cannot solve it at that time. But now after 20 years, it is essentially, I mean, I need to refresh my memory on some of this. But yeah, so for planar graph, we know that there is always a vertex of degree 5. What's the meaning of that? So it means that you can just remove this vertex. So consider, first, if you consider any induced subgraph, it is still planar. Correct? And then why it is bounded, why the average degree is bounded? Because you know that there is one vertex of degree at most 5. Remove that vertex, the rest is planar. There is another vertex of degree at most 5. Remove that. You can't do that until you will remove the whole thing. So it means that the average degree is at most 5. Good. And that means that planar graphs, which are H minor free graphs, are indeed bounded arboricity graphs. So bounded arboricity, almost, I mean, this is the most general class of graphs that we are considering. And these are, like, again, very sparse, a very general set of graphs, very general set of sparse graphs. That in general, these are the graphs that the number of edges essentially are linear in the number of vertices. But this is essentially a sparse graph. There are some other sparse graphs like expanders. It's like, I would say bounded arboricity is one corner sum of. So if you consider a sparse graph, there are two things that are there. So one is the essentially bounded, essentially expanders, bounded expansion. These are one, and the other one essentially is this kind of bounded arboricity. And this bounded arboricity contains H minor free graph, planar graph, bounded genus graph, and a few set of graphs. There are some other smaller things essentially. Maybe there are some intersecting things, but these are like currently the main things that there are good general results like this. Here it goes to H minor free graph. Some of these things can be generalized to bounded arboricity, not everything. But bounded arboricity is a very interesting thing again, because you can say that if you consider a graph, any induced subgraph that you are considering it has average bounded. So what is the thing? So in some sense, this is a more recursive version of a sparse graph. In the sparse graph, say that, okay, the whole graph should have a linear number of edges. Here in the bounded arboricity, that this should be correct recursive. For any induced subgraph, also you should have this problem. So what is the thing? So essentially it says that you cannot, so this is the whole idea, is that you cannot have generally a sparse graph And inside that, you may have a clique of, say, square root of n. This is not possible in bounded diversity graph. Why? Because, I mean, here the number of edges, this graph is essentially average degree is constant, or has a linear number of edges. However, this clique is some kind of nonlinear part there because it has essentially a very dense graph there. There's some other thing they will call it everywhere sparse or something like this. But this is the whole idea of in some sense, bounded diversity graphs are very general set of sparse graphs are very practical set of graphs because almost all cases we have like linear number of edges. The only issue is this one that it asks for it to be correct recursively. And if you have a clique of a square root of n inside a graph of size n, which has a linear number of edges, it's essentially a planted clique, then this graph is not a bounded diversity. So it still has a linear number of edges. Okay, so that's essentially general ideas that we are talking about, why we are talking about, because of the practicality of this bounded average degree and because of all these properties. And there are tons of essentially graph theories developed for this. Again, this is the deepest by far, essentially, factor 2, 3 of any other theorems that we know for graph theory. Even, I don't know, after how many years. Good. So one thing that actually plays a lot of things there, this is the concept of Treewidth. The Treewidth is another thing that there are, if you want to just see the definitions of this, there are, I don't know, 10 equivalent definitions. The people obtained through different contexts, they reach to the same concept, essentially. So in that sense, it's a very beautiful thing. And again, this is like the same idea that we want to solve the problem. We cannot do it in general graph. What can we do? Let's solve it on trees. And then this is some generalization of trees. So the treewidth of a graph is the smallest possible width of a tree decomposition. So you need to consider all possible tree decomposition of a graph. And the smallest possible width of any tree decomposition would be the treewidth of the graph. What is a tree decomposition? So the tree decomposition is a way to represent a graph as a tree. So tree decomposition, I mean, you can define it for arbitrary graph. Good. But the width of that, it would be bounded treewidth. Generally, when we say bounded, means constant, essentially. Sometimes you can handle up to log as well, but it should be bounded. Generally means constant, but sometimes up to log is also correct. So what does the tree decomposition is that? So the tree decomposition is that we are given, essentially, for this graph, we should have a tree such that each vertex here, each vertex in the original graph, for example, here, should be, it is called smeared as a subtree of this tree. Good. So, like you want to get a tree decomposition, get essentially we have a tree. How do we get this? This is like you can think about this FRT or Bartle or other things. They are not necessarily subsets of the graph. It's just some tree. Such that each vertex you can smear it. And this is the mean, like essentially smear it as a subtree in this graph. Or essentially means that each vertex has a subtree in this graph. What is the property? The main property is that so each vertex has a subtree. That's the main thing. Any two adjacent vertices should have overlapping subtrees. Good. So in some sense, you are just representing the whole things as a tree. And you, what was that? If they have overlapping, no, just one way. You can get some kind of similar to metric compilation that has this.
But if you just want that, then why can't you just use the
You want to minimize the width of it. Oh, what is the width of it? The width of it is the maximum overlap minus 1. Actually, there is this concept of the same thing that you mentioned. We are doing metric completion on the graph. You can do some kind of completion also for tree decompositions, that you will get a graph which is essentially super graph of this graph. It has more edges and it still has the bounded trees. The same type of completion, we can do it here. You try to maximize the overlap. Yes, of course. I mean, this one you can overlap everything into just one vertex, but then the width of it would be essentially if the maximum overlap is n, because n trees are there, n minus 1 would be the width of it. And indeed, so this is the definition. This is a tree. You want to embed it such that every two vertices that they essentially are adjacent, their corresponding trees, they should share a vertex. And you want to minimize the width of this tree, and the width of it is the maximum overlap minus 1. In particular, Treewidth 1 graph. What's that?
Overlap
on the vertices. So Treewidth 1 graphs are trees. Treewidth 2 graphs are series parallel graphs that I have mentioned. I mentioned previous time that like a series parallel graphs are the graphs that essentially you can. These are like the resistors essentially graphs. That if you have two graphs, like this one, any graph has a start, and this you can put it essentially. This is the first graph, and this is the second graph. So you can put this graph. So this is AA prime, and this is BB prime. You can consider these two graphs and make them essentially you can make A and B the same and A prime and B prime the same. This is the parallel. Or you can make A prime and B the same. This would be series. These are called series parallel graphs. And series parallel graphs, again, are very important because these are the graphs that have both bounded Treewidths, Treewidth 2 in particular, and they are also planar graphs. So interestingly, you may think about planar graph may have a bounded Treewidths. No, they don't have a bounded Treewidths. I will talk about it. But here, this is the thing that I wanted to say. So what are the important things about the graphs of the graphs and their important graph regarding Treewidths? Treewidths of trees is 1. So this is by definition, essentially, any tree has only Treewidths 1. Series parallel graphs, these graphs that I have mentioned, the resistors graph, they have Treewidths 2. Clicks, a click of size n, or essentially kn, the Treewidth of it is actually n minus 1. As you can. So that's the ultimate things. Now, one more interesting thing that I wanted to say are for planar graphs. As I mentioned, the whole idea of this bidimensionality is that planar graphs are somehow grids. And this grid so this is essentially a square root of n by a square root of n grid that has n vertices. The Treewidth of this is actually a square root of n, or order square. So in general, and this is a planar graph, correct? A planar graph of n vertices. For planar graph, the Treewidth can be at most a square root of n. And it can be a square root of n. So why these series parallel graphs are important? Because, as I mentioned, generally the people make these mistakes. Planar graphs, they don't have bounded Treewidths. They can be actually very large, a square root of n. But it is important that so these are like they can be as large as square root of n. But series parallel graphs are the graphs that are both planar graphs and bounded Treewidth graph. And if you remember, these graphs, a diamond graph was for the Bartal embedding. A diamond graph was the graph that you couldn't get better than log n distortion for that. And what was a diamond graph? Diamond graph was a series parallel. So these are some of the important things that I will talk about here. If you work on the graph, these are important things. diamond graph, or in general, series parallel graphs are very important because it's like both planar graphs and the series graph. The other one is important if you want to work essentially on a sparse graph. Either grid, you may start, okay, you want to solve the problem, start with grid, or the other one is the bounded, essentially expander graphs. So these are the graphs that they have bounded expansion. I mean, we may talk later in this course, but generally bounded expansions, I think the general ideas there, these are also some kind of trees. If you consider essentially consider each vertex up to essentially the distance log n from this. So this is for expanders or bounded expand. Essentially, expanders, we are considering bounded expansions for them. For these guys, if you consider any vertex, so what are the expander graphs? The expander graphs essentially are the graphs that if you consider from each vertex, and you will consider up to a diameter log n, this looks a binary tree, or maybe ternary tree or something. So for each, like if you consider each vertex, from local v of each vertex up to some diameter log n, it is like a binary tree. So everything is, we are talking about trees essentially. Always there is some trees playing a role, because we can solve the problem on trees much better. These two are important. Expanders and the grid graphs are important. If you want to work on it, on a sparse graph, you want to prove it, you need to prove in these two graphs, at least. Sometimes you may need more work, but generally these two should give you very good ideas about sparse graphs. Good. But that's essentially about this. Now, what do we know for trees? So, but why do we care about the Treewidth? Because these are generalization of Treewidth graphs. In particular, for lots of NP-hard problems on graphs of small Treewidths, we have a running time 2 to the order Treewidths n to the order 1. So if Treewidth of the graph is the parameter of the graph, then essentially this is like you can say there are fixed parameter algorithm for that. So for many NP-hard problems on graphs of small Treewidths, you can get actually polynomial-time algorithm. Why? Because in general, if the Treewidth of the graph is anything like Treewidth, then the running time of this dynamic programming. So these are generalization of dynamic programming that you are doing on trees, and that would be 2 to the order Treewidth n to the order 1. It means that if the Treewidth is bounded by some constant, and actually lots of the case even log, even Treewidth up to log, you can still solve the problem in polynomial. Computing Treewidth itself is NP-hard. So you cannot do that. However, if you want to compute it exactly, this is like the one that we have, 2 to the order Treewidth. It's the best that we have it so far. 2 to the Treewidth, you can actually compute a Treewidth of the graph. Exact Treewidth of the graph. And we don't know. If you want to get order 1 approximation for that, actually you can get 2 to the Treewidth to the n to the order 1. If you want to get a constant factor, you can actually do that. And both of them also, they give you the tree decomposition. But the best existing algorithm for that is the one that we have it actually. This paper is actually cited quite a bit. This is order square root of log opt. Before us, it was log n approximation. This one is a square root of log opt approximation in polynomial time. Opt is Treewidth. So, there are two things here. Of course, first is square root of log, not log. Second one is square root of log opt. It means that if the opt is constant, then this would be a constant factor. This is the paper that we are using a new framework for new frameworks at that time for vertex separators. Based on embedding with minimum average distortion. So this is the idea that we are doing essentially. Here we were talking about distortion into the distortion essentially into trees. Here, to obtain this, we need to get vertex separator. We talk about vertex separator later. But to get the vertex separator, we are using embedding into minimum average, like we are doing a minimum average distortion into a line. And I mean, for vertex separator, there are some examples that this comes also from some SDP. And this SDP essentially, the integrality gap of that is the square root of log n. So probably, I mean, for a long time, the people cannot improve this. Because this vertex separator are almost equivalent of Treewidth. And there, you know that you cannot get better than a square root of log n approximation, or square root of log up. So that probably remains for a while as the best approximation to get essentially, if you want to get polynomial time for Treewidth, that's the best that you can do. Now, if you consider planar graphs, and this is like something like single crossing minor free graphs. So single crossing minor free graphs essentially means that a minor free graphs that exclude a single crossing. Single crossing means that you can draw that problem essentially on the plane with at most one crossing. And this is single crossing minor free, it means that the graph that excludes it. So essentially planar graph and the slight generalization, that essentially is the one that there exists a 1.5 approximation for this graph. These are some of the papers there. But for general H minor free graphs, there is order V of H to the 2 approximation in polynomial time in like H minor free graph in the same paper that I have mentioned. That algorithm, actually, you can say that when you are talking about H minor free graphs, you can get order V of H to the 2 approximation. And so it means that if H, so generally when we talk about H minor free graphs, H is a constant. So here it means that for the constant H, actually you can get a, so for a constant H, you can get a constant factor approximation. So for H minor free graph, we can get a constant, but for general graph, we can get a square root of log out. Now, having said that, I think these are some of the basics of the things. Good. Now let's define the bidimensionality. So we are talking about this kind of closed properties a lot. A parameter K is called minor bidimensional if it has 2 properties. It is minor and bidimensional. For the minor part is that it should be closed under minor. It means that K does not increase when deleting or contracting edges. So here, this is, I mean, again, deleting an edge or contracting an edge. This is called essentially minor bidimension. Like a minor, it should be closed under minor. We will talk about what is this parameter K in the sense of, like, for example, fixed parameter. The other one, it should be large on the grid. What's the meaning of that? It means that for an R times R grid, size of K should be essentially omega R square. Or in general, it should be some function of f of R. There are some of them, actually, this f of R is just log of R. We will talk about that. So it should be somehow dependent on R. I think this is a very natural thing. We will talk about that. Let's see this example. K is the minimum number of vertices required to cover every edge on either endpoints. This is a vertex cover definition. So generally, K is essentially we are talking about for now we are talking about unweighted graph. K is essentially the size of the optimum solution. So here, if you let K to be minimum number of vertices required to cover every edge on either endpoints, then of course, I mean, here, this is an example. So this is a coverage, this is a coverage, this is a coverage, but this is not a coverage because no one covers. So this vertex cover, this parameter K, has these properties. It is closed under minors. Why? Because if you delete a vertex, if you delete an edge, you don't need to add any more vertices to the vertex cover to satisfy it, because it's already satisfied. You just delete it. You just make the things easier. It is not always the case, as we will talk later about dominating. So you may actually here, even by deleting or by contracting, actually you may go even under, like you may decrease by 1 even. Not only you don't increase, but you may decrease. The other one, it should be large on the grid. These are both of them are very easy to check. That's the whole idea. This was again the beauty of this Robertson scheme, or for minor closed property, that the graph might be, very essentially the property might be very complicated, like planar graph. Checking the graph is planar is not that easy thing. If you want to write a program, try to write a program. It's not an easy thing at all to check it essentially. There are some algorithms for that. These are not easy. You need to consider lots of case analysis. How you can, this is the case, if there's a degree of vertex degree 1, then you should do that, degree 2 or something like this, then you should say that they should be at least reconnected, etc. There are lots of case analysis that you need to do that. So it's not a trivial thing. But this one essentially makes some kind of meta theorem that makes everything like out of this kind of case analysis. So this is the same thing. This minor clause is that any minor clause property, you can decide it in polynomial time. The same thing here. Here we have just two properties that you will check that, then you will get, that there is a PTAS for this problem on this class. You have a fixed parameter algorithm. And it is almost essentially if and only. It is almost, it's not exact, but generally, if it does not satisfy, we cannot get these results. So why it is large on the grid? It is very easy. If you consider essentially matching on these things, from each of these edges of this matching, we need to cover at least one vertex. This one vertex from each edge should be in the vertex cover. So it means that the size of this is omega r to the 2. So the size of the vertex covered is actually omega r squared. So it means that vertex cover is a bidimensional property. There is another one also. It is called, this is the version 2. So this is one thing that we are doing in bidimensionality, which is minor closed properties are the one that has been used a lot in Robertson scheme. But one thing the novel thing about this bidimensionality that we created essentially is that we are talking about the theory of contractions. That it may happen that the property is not minor closed, but it is contraction closed. So let's talk a little bit about it. So a parameter K is contraction bidimensional if it is closed under contractions only. It means that a K does not increase when contracting edges. What's the meaning of that? It means that if you delete an edge, the size may go up. And that is, again, this contraction is something that was essentially this kind of contraction clause is absent in Robertson scheme model. And this is the bidimensionality actually word that is considered. The same thing, it should be large on a grid-like graph. What is a grid-like graph? It means that for any natural triangulated R by R grid graphs. So consider the grid graphs, and just triangulate it. For any triangulation, it should be large. Again, it does not change that much the problem. There are some more standard way of this essentially that make it a nicer triangulations as well. But essentially, it is a grid graph. So this is, you can think about planar graph, it's this grid. Maybe like a little bit more structure of that you want to preserve it, it would be triangulated. Let's see the example here. The dominating set. So dominating set is very important. What is the dominating set? Minimum number of vertices required to cover every vertex or its neighbors. Good. Minimum number of vertices required to cover every vertex or its neighbors. Why this problem is so important? We have seen very important problem essentially that the covering problem was super important. Which problem? Set cover. Dominating set essentially is equivalent of set cover. Why? I mean, what's the meaning of that? You want the minimum number of vertices required for every vertex, or it's to cover every vertex, or it's essentially one of its neighbors. How can we solve essentially a dominating set using a set cover? Yeah, I mean, essentially you will define the sets. The sets would be essentially a vertex and its neighbors.
How would you solve set cover?
Well, I mean, one easy thing is that essentially, if you consider this one, the bipartite version is easy. So, so the bipartite version is that essentially this is a set cover. So you want to select a set of things such that each part in the second one is dominated, essentially. Correct? And then you can add this to make it from bipartite to essentially general graph is not that hard. That's essentially the idea. But the bipartite case of set cover is essentially the bipartite case of dominating set, the set cover, and it is easy to get for general graph. So dominating set and set cover are equivalent. So this is a super important. Now, again, so this is the dominating set. For example, if you consider this vertex, if you have one vertex, you are in a good shape, this is a good shape, this is a good shape, but this is not a good shape. If you have these three vertices and none of its neighbors are covered, then it is not good. Now, the important things here is that this is large on the grid. Again, to see that in the grid, as I mentioned, triangulated grid, but doesn't mean anything. If you consider, like, if you just partition, this is the typical thing, just partition this grid into these cycles of length 4, even if you consider triangulated, from each of them, you need to at least select one vertex. So it should be omega r square for a grid of r times r things. But this is the interesting thing. This problem, dominating set cover, this is actually somehow one of the probably set cover and say, for example, SAT. These are some of the basics of computer science. Lots of applications. So this problem, this motivation comes that this problem is not closed under minor, but it is closed under contraction. So if you contract the vertex, yes, still it is a coverage because you didn't lose anything. But if you deleted one vertex, this might be the case that this vertex covered this vertex. Now, because you deleted this one, someone else should cover this. So it is not closed under deletion of only closed under contraction. And that was the whole idea of bidimensionality theory, that we consider this one as a problem that is somehow this concept of theory of contraction instead of just minor essentially. And of course, if the problem is contraction closed, is also minor closed because it satisfies both of them. So a bit essentially more general things. Contraction closed is more relaxed because it should be closed only under contraction, not necessarily deletion. So there are lots of contraction bidimensional problems. These are just some of these, essentially face covers, minimal maximal matching, H dominating set, R dominating set. TSP, this is another one. Metric completion, there are lots of others, and the people have developed more. Another very important one is actually is diameter. Diameter is another parameter which is contraction closed. If the diameter of the graph is K, and then if it contract edge, it would be remain at K. But if you delete an edge, the diameter may go up. This is like a very important parameter of diameter. Actually, there was something about defined about the local Treewidth. So there was this concept of a local Treewidth was defined using the diameter as the parameter, and the previous bound was 2 to the n, essentially the bounds that they had it. We could get this bound all the way from that to linear because of this bidimensionality of diameter. So it was like from double exponential, you get the optimal linear. TSP is another one, essentially, that if you have a tour, if you contract it, then it goes down. But if you delete it, then it may go up. So this is like lots of computer science, essentially, things for that. Now, what do we have? This is the main thing that let me just see. So this is the first theorem that we have it here. Which is the main theorem. If a parameter K is bidimensional, then it satisfies this parameter Treewidth bound. What is the primitive? The Treewidth of the graph would be at most order square root of K. So if a parameter K is bidimensional, then, I mean, minor contraction closed, then you can say that it satisfies this one. The Treewidth of this graph will be bounded by a square root. And this is correct for any graph excluding some minor. This is the main bidimensionality paper, and this is the combinatorics is the top journal in combinatorics. That was the JC. What is the idea? This is the idea is this one. If it has a large Treewidth, so we want to say that the Treewidth is bounded by a square root of K, and not just K, a square root of K. The idea is this one, that essentially if the graph has large Treewidth, then we know this is something that we know from minor theory, that it has a very large grid as a minor. So if the graph has a large Treewidth, then we know that it has and here we are, talking about this always we have this bond essentially. This is bonded, and there's several recent work on these things. The best bond for general graphs, but we are talking more currently for H-minor graphs. This bond is linear. So if you have a Treewidth, if the Treewidth is R, then you have an R by R grid as the minor in this graph. Then, of course, as I mentioned, so we know that there's a very large grid there. Generally, as I mentioned, that on this graph, like for example, for dominating set or vertex cover, we knew that if we have R by R grid, the size of the parameter is R square. So essentially, this square, this square root is coming from this square. Because you know that if the Treewidth is essentially proof by contradiction. You say that if the Treewidth is larger than this, then you know that there's a large grid there, and on this large grid, then you have essentially, you know that because the grid is large, then the size of this parameter would be large because it should be omega of r. So if essentially if the Treewidth is greater than square root of k, then we know that there is a square root of k times square root of k grid. And then we know that in this case, you should choose constants correctly. But then you can essentially get, is this square root of k, square root of k? Then it means that you should have a solution. The solution size would be square root of k to the 2, which would be k, which would be larger than that. That would be essentially the contradiction. So this square root comes from r squared. By putting some constant here, that if the Treewidth is larger than some, I don't know, c times k, then, and this is order. So if it's larger than c times k, it means that there's a large grid there, and then that constant can observe the constant here, and essentially you will get then you get a contradiction because the original graph actually is a larger things than k. Okay. So this one also so this is like the main structural theorem that exists essentially for parameter and Treewidth, and it relates the Treewidth of the graph to the size of the parameter. Now, for example, for fixed parameter, the life is very easy. Why? Because we know that this graph has a bounded Treewidth. So if the Treewidth of this graph is at most square root of k. Now we know that this is essentially this one. If a parameter k is bidimensional and it is fixed parameter tractable on graphs of bounded Treewidth, which is always almost the case, it is h of Treewidth, and this h of Treewidth generally is 2 to the Treewidth. It means that then it has a sub-exponential fixed parameter algorithms. H of square root of k, that essentially means this kind of sub-exponential time algorithm, 2 to the square root of k times n to the order. And this is the best that you can get until under ETH, essentially. So the fixed parameter just comes from that Treewidth bound. And again, this is the algorithm. Run the bounded Treewidth algorithm on this graph. And if the Treewidth is larger, just say no, essentially. And you can get a constant factor approximation for Treewidth that actually would be enough here, because the running time of that was 2 to the Treewidth. That was not that bad, essentially. Anyhow, we have 2 to the Treewidth here. So this is the idea that like we can get actually lots of fixed parameter algorithm just using this one, just because the parameter is bounded, this you can get it. Not only that, yeah, so you can also get lots of PTASs. You can get 1 plus epsilon approximation for these things, because essentially the Treewidth bounded things give you some kind of vertex separators, and these vertex separators you can actually get the PTASs. So I will stop here, and then we will talk more about these applications next time and beyond this essentially.